also on unstructured spherical grids, but using logarithmic reconstruction. Okay.
So every morning, every day. This is a joint work together with my diploma student Katharina Elsen, and it's the first approach to have some advection schemes on unstructured grid on the plane and later on also on the sphere. So in the talk I will give short introduction, then I will explain what is this type of logarithmic reconstruction on one-dimensional grids. It's already a known method, and then I explain you how we have that generalized to this type of unstructured grids, give some numerical results and some conclusion and outlooks. So what we want is we want to solve hyperbolic equations on unstructured grids, which are decomposed by a polygonal convex grid. And what we have are cell averages of the unknown function in all the grid cells. And the goal is that we have some type of indirect approximation of this integral formulation of this conservation law on this type of grid structure. So, and the idea is in 2 dimensions, we have this type of grids. First, we have, in each grid cell, we want to compute a function Rk, which uses all the averages of this grid cell and all the surrounded averages. After that, if we have this function, we compute at the edges, or then in 3D at the faces, we compute an approximation of this reconstruction at all of these faces, and after that, we compute a numerical flux function from this from the values from the left and from the right, and in the case of the advection equation, we take simply the upwind value from these 2 values. So this is the idea what we want to do. It's classical, and then we apply some kind of a Runge-Kutta method to integrate that then later on in time. So now, what is this type of local double logarithmic reconstruction? This idea was introduced by Advection and Schroll, I think at the end of the last century, something like that. And in 1 dimension, so we have here through neighbored cells. The first thing what we do is that we compute some approximation of the first derivatives at these 2 boundaries of this inner cell. This can be done here in 1 dimension by some type of finite differences, and what we need is that they are something like of second order accuracy. After that, we take a function of this type, so it's the combination of a constant and two logarithms, and at the moment we have here 5 free parameters to construct some function in this inner cell here. We have changed a little bit the notation in contrast what you find in the paper by Advection and Schroll. So we write now first a function phi k, which is only these 2 logarithms, and you see here that we have here one where you can think lives on the left side on the face, and we have here so that this part here is positive, and this function lives on the right hand side on the face. And now we have here only one constant. This is some type of a shift. So that in all cases, also if we live at the boundary, this shift is positive, so that this argument is positive, and we have two free parameters b1 and b2. With this function, we construct now this function rk of x, which is the cell value plus the function minus this function integrated about this inner cell divided by the grid length. And with this type of ansatz, we already have that this function rk has the same cell-centered average as ck. So after that, we have to think how to choose this shift parameter. So we have altered that a little bit, changed from the paper. So the idea is that the shift parameter should depend on these two derivatives, and first, these shift parameters should work in the following way: if these two derivatives are equal, so this means at first one the function is linear, or you have there a local maxima or minima, then we want, at least for a linear function, we want to have a shift that we also get some type of a linear function. So, and there is a proposal in the work by Arterbrand and Scholl that you compute something of the shift, which is a harmonic mean of a scale derivative of these two derivatives. And this shift parameter has the property then that if these two values are equal, it goes to infinity, and on the other side, if one of the derivatives is larger as the other, so you have some type of a singularity there or shock, then this parameter goes to 0. We will see now how this works in practice. So after that, we have, if we have chosen the shift parameter, the next thing what we have to do is we have to determine these two free parameters in this function phi k, and we choose that in the following way: that our ansatz function coincides at these two at the left and at the right hand side of our inner cell with this estimated first derivatives. And then you can show that if these derivatives are of second order accuracy, then this reconstruction for a given function will agree with that function with third order accurate then. It's something like some type of Hermite type proof to give a proof for that. So now I want to show with some pictures how this works in practice. So here at the first one we have three data which are linear, and then also this function the reconstructed function is then also linear. And if you zoom out from here, then you see that the poles, this type of shift, lies somewhere outside of this grid where we make the reconstruction. So another type, if we have a minima, then we get this type of reconstruction, and you see that both of the poles are a little bit outside, but you have this type of symmetry also, and you have this minima. And the other one is then, if you have this type of the singularity, then the function is reconstructed in this way, and this second singularity sits somewhere here. So we have here zoomed in, and you see that this type of is somewhere sitting here. So okay, this is so. And if you then look for a function in the full sense, to see how this small red functions are approximate this smooth function. Now we go to the to our unstructured grids, and now the idea is to do the same in a similar way. So first we need approximations to the directional derivatives at the cell faces, and that we also want to compute from the cell averages. So for each of this edge in 2 dimension or a phase, we need a directional derivative at all the phases, and with this multiplied flux approximation, this derivative is computed from a reconstruction of the gradient in this node with all the cell-centered values which are connected with this node, and also with this node. And this is a method which is usually used to discretize diffusion equations on unstructured grids. After that, we also choose an ansatz function, and this ansatz function has in some sense the same structure as in the one-dimensional case. So we have, for each phase, we have a free parameter. We take the normal of this phase, multiply with the difference from a point in the cell and the midpoint of the phase, and we have then for each phase a separate shift parameter. So it has the same structure, and you have here a logarithm of an affine function. And with this function, with this ansatz function, then we construct in the same way this function rk. So it's the integral of that minus the function, so that we all cases have that both functions have the same cell-centered value. So the next thing is how to choose this shift parameter for each phase. And here our first idea that we have at the moment are implemented is that we take our cell. So we have an ansatz function which is connected with this phase. And now we looking for a point which we go in this normal direction and looking for the intersection with our grid cell. And then we compute also here a gradient information from all these gradient informations which we have here at the midpoints via a barycentric interpolation. And then we have now for each of this ansatz function, we have now two derivative information in this direction, and then we choose in the same way as in the one-dimensional case the shift parameter now from this di and from this large di. So the next one is to compute these parameters bi, and that is done in the same way as also in the one-dimensional case. So we are requiring that the gradient of our ansatz function multiplied by the normals in the midpoints of the phases is equal to this directional derivative. So this is a simple linear equation where you can solve for all the bi's. The next one then is to compute these phase values. So we have to integrate then our ansatz function about this function rk at some of these phases, and then we get our phase values. And the nice feature is that if we assume that all the phases are planar, we can compute this integral and also the integral which we need for the construction of the ansatz function. This means this integral. Both of these integrals can be computed exactly. And the idea is that if you have a if you have a function like, for instance, log t, where you can also can integrate this function. You can have the first integral and the second integral, and and the argument is an affine function. Then you can calculate this integral via the divergence theorem, and then you can go in 3 steps. So you go first from a volume integral to surface integrals, where you take this type of function to describe psi null as the divergence of a vector field. Then you go to surface integrals, and then you take the surface integrals and describe this function psi1 in this form with this ansatz, and then you take you take Stokes' theorem, and you have integrals on the edges, and after that you have to integrate on these edges, and then you get, and the same you can do in a similar way for the phase computation. And what you see is that you have to compute this logarithmic function for all phases and for in all of the node points, and because we have this number of nodes and this number of phases is the number of ansatz functions, we have to compute in logarithm in this number of times, and then you have to compute then these functions to compute that. So, and to see how this function then looks like in 2 dimensions, we have here different type of values, and then you see how this here is this is the grid cell here, and then you see how this function lives in this grid cell. So now we are going to numerical tests. So we have tested then this idea on 2 grids on the sphere. So we have a cube sphere and an icosahedral grid, and we have made an advection of a cosine bell of a slotted cylinder around the equator, and then an advection test of this deformation flow, which was shown in the talk before. So what I want to say is that the computation is done on the 3-dimensional grid. This means we have first this grid on the sphere, then this grid is inflated so that we have two spheres, and after that we have this 3-dimensional grid, and after that all the ideas about sphericity is not further taken into account. The problem is then that some of the phases are non-planar, so some of the formals which I have described before are not correct, and the time integration is done with the third order as a Spiro-Kutter method. So this is, here you see the convergence order. This is this cosine bell test for the icosahedral grid. The same, you see not that much for the cubed sphere. Then we have done this slotted cylinder test, and then this with this shaped with these two Gaussians. So, and my conclusions is, at the moment we have an ansatz function. We have no use of limiters. We have with this function the total variation of the function somewhere under control. Only nearest neighbors are needed. Also with this ansatz function local extrema, at least in 1D, also in this can be reconstructed. Linear values also in the 3D case leads to linear functions, and at least we have observed third order convergence on Cartesian grids. See the poster. Thank you.
Talk, any questions?
Yeah. You mentioned you're not using any limiter. So is your scheme positivity preserving?
At the moment, not, because you can have this ansatz small undershots also in the one-dimensional case, and then you have to introduce something like, and you want also to do something of that. You have to introduce something that you get positivity. So you have to combine it with the first order method or something like that, and then this maybe is. So because it's not clear that the function that they can be a little bit negative, or you can make at least a large step or something like that you get small negative values. That is not. But what you not get is maybe a type of oscillation or something like that.
Any other questions? I was wondering, I think Advection and Schroy, they also did or used or tried other ansatz functions with more free parameters, and if it would be possible to use something for example.
I think this is I think this type of ansatz function are the latest one that they use. First they work with this hyperbola, then they use only one logarithmic ansatz function, and then they are take two, and the idea is you have two monotone functions, and then you can combine these two monotone functions. If you have monotonicity, you take both that they are in the same direction, and if you have a minima or a maxima, you change the monotony of one of these two functions. This is the idea there. So if you see, you can also take, I think, some type of ansatz function which has this property to get something similar. So that's my inspiration, but because this computation of all this logarithmic function is not that cheap. But all other things you can compute in advance, all the factors or something like that. You have to, in that integrals you can compute once, and then it's only a computed function, and you have to multiply it with the matrix. And also this MPFR is only you can compute in advance, and it's also only matrix times some values.
Okay, there's another question.
If the singularities of the functions are outside the cell, could you not use a simple rational approximation? That would be a lot cheaper, and then, like a PDE approximation.
Maybe. I think there's some freedom, because now in this knobs ideas what they take now, there you have in this new finite element stuff, you have all this knobs function where you take it for describing the grid, and also as an ansatz function. So where you can maybe play also with this type of function to do here something.
I was just wondering, when you switched to your test cases, you had very small convergence rates, at least for the L infinity norm. Is there hope that you get better results for the sphere?
What means
for example, here you have L infinity, well, you have no convergence in the L infinity norm.
Yeah, as I think this is a little bit connected here with this, as in the cubed sphere, I think a little bit connected here with this border. But we have not checked it all in detail at the moment, so that's a work in progress.
Okay.
So we have done that. It was a hard work for me to have that all on the computer to work. And I had also to mention that for this equilateral grid, there's no optimization, so it's only starting from this first grid and dividing, and no further optimization or something like that. It's only grid where you get it from this division.
Okay. Yeah. Thanks to the speaker again. And